Welcome to Lecture 12. Today we'll be discussing the principle of virtual work as is applied to 3D, three-dimensional problems. And now we're covering chapter 6 of my book. So let's look back again at the 15 equations of elasticity. We have the three governing equations, the equilibrium equations, then we have the 6 strain deflection relationships, which relate the strains to the deflections. And then we have the 6 stress strain relationship, which relate the stresses to the strains through Hooke's law for isotropic material or the fourth order anisotropic tensor. So as we can see here, we have 15 equations, 15 unknowns, 6 stresses, 6 strains, and 3 deflections, 3 displacements. So 15 equations, 15 unknowns, and that's what we found earlier. We also talked about the boundary conditions. The boundary conditions are displacement specified at the boundary, which is ui equals ui bar on part of the surface. And then let's call this on surface V1, and this is V1. And then we also could have traction forces applied on the surface of the structure, and we're going to call that as applied to on V2, for example. And we can use Cauchy's relationship with that. So that's going to be sigma ij and I equals Ti. Okay. So that's what we found. That's what we discussed. And so from there, what I want to do now, I want to now remind you what the equilibrium equations look like in a different format. These are the 15 equations. Here I have 6. And you can see here, these are the green Lagrange strain tensor right here, which is symmetric because if you switch I and J, you get the same answer. And the stress tensor is symmetric because of the symmetry, because of the conservation of momentum. And then we have the 3 equilibrium equations. And there are 6 stresses that are known, 6 stresses that are unknown, and then 3 displacements are unknown. So 15 equations, 15 unknowns. And to solve these equations very simply, all we need to do is substitute epsilon ij here. And then once I have sigma ij in terms of deflections, I can substitute that here. And then that will give me a highly coupled differential equations, partial differential equations. So now moving forward here then, let's cover now the principle of virtual work. And so let's discuss the principle of virtual work, and we're going to apply calculus of variations during this particular problem, and we're going to discover some amazing things. So before we use Newton's law to derive the equilibrium equations, but I'm going to show you how the principle of virtual work, when applied to different problems, can get you to the same answers, or when you make mathematical simplifications to a theory, it can give you very similar answers as well. So let's start with calculus variations. So let's presume actual deflections, actual displacements. Reach unique values. And I hope you're taking notes real time. Corresponding to a body in equilibrium. Now consider very displacements u tilde x. So let's say that u are the deflections that we have in the body. And so then we have a virtual deflection. So we define virtual displacements del ui of x, right? So we're going to define that at a fixed material point. That is, we superimpose arbitrary virtual displacements throughout the body. And I'll discuss this a little more. What are we saying here physically? This will vanish. So this arbitrary virtual variations vanish at locations where displacements on the surface are specified. In other words, if we have a body of material and I apply loads to this body of material, body force BI, traction forces TI, and so forth, and maybe even accelerations, what we're saying here is that if this body is in equilibrium, we will consider varied displacements so that at every point which has already deflected amount u, we're going to consider a varied deflection from that point. So that's an arbitrary virtual deflection throughout the body. These arbitrary virtual deflections have to go away at locations where I actually specify the boundary conditions, because if ui equals ui bar, then del ui is 0 at that location, because I cannot vary something that's specified. So when that happens, we call that the virtual displacements are kinematically admissible. Anytime you see that being discussed, we're talking about the virtual displacements being kinematically admissible. So if I look at the virtual work or the forces acting on the material point, so let's look at the virtual work. It's not real work, it's a virtual work. The virtual work of forces, and I apologize for that, acting on the body. So if I want to calculate the virtual work due to the forces acting on the body on a material point, then the external virtual work, I'm going to call this the external virtual work because that's external virtual work done by the external forces. And I have the body force BI, so that's BI del UI dV, right? Plus integral partial V TI n del UI ds. And I also could have accelerations. Those accelerations could be acting on the body, and they could be considered inertial forces acting on the body. That's a possibility, and that does occur. So, you know, why is this external virtual work body force times del UI? Why is that? Because if you had a block of material and I push a block of material at distance d with a force F, then the work done due to this is F times d. And if I did a virtual, instead now I did a virtual or fake small amount of deflection moving that block with a force F, then there'll be a virtual work times F times del D. But because BI is per unit volume, that's why I had to have the integral here. But we have basically the same thing as you may have seen in physics. As well here, you have tractions applied on the surface. That's traction per unit area. That's why I have to integrate it over the surface. And I have to multiply by del UI at that location, at that particular location, which I'm gonna call del V1. So it's very clear that that occurs there, but I don't have to do that. But I'm doing that to show you that that's a possibility. And del V1 covers this whole surface. It can cover this whole surface, all this surface here, all that is covered, okay? And then in addition to that, I could, and in reality, I can break up the integral into two pieces, one for partial V1 and one for partial V2. We know that one vanishes because del UI is zero at that boundary, but I'll write it here so it's clear that I broke up the surface, and I'll add them up together in a second, but I want to show you that this is zero right here. That this third integral here is zero because this right here, which is del V2, the deflection displacements have been specified. At other locations where we have partial V1, that surface that's not partial V2, that surface where tractions are applied. But where partial V2 is, UI equals UI bar, that has been specified. So therefore, this integral is zero, but I'm putting it here so you can see what it looks like. You can still put it there. We know it's zero. It's not a problem. I'm going to take this further. I'm going to say there's even an inertial force acting on this body of UI double dot. And that'll be nice because we can then look at even, maybe even looking at a more advanced theory where we're including inertial forces. That's one way we could do this. And it can be beneficial. We can do that. It shouldn't be a problem doing that. So minus, we can add the inertial quantities on virtual external work, because inertial forces do act on the body, and that'll be even more general. So then we have rho, for that rho ui double dot del ui dv. And you may ask me, why is that? Well, this rho times dv is mass times acceleration is force. So yeah, this is correct. This is the mass times acceleration dv, and that's acting on the deflection at every point of the volume. So as a consequence, that contributes to the virtual work done by the external forces. Now, again, you in physics probably learned the work done by force applied to deflection. Here, we're advancing that theory even further and now considering these deflections to be virtual for a very particular reason. We're going to apply calculus variations to solid mechanic problems to determine what are the equations of equilibrium. And I'll demonstrate for you that those are going to be the Euler Lagrange equations, which is very powerful. I have not used here. Have you seen me use here Newton's law? No, I have not. So that's very powerful. I'm going to be able to derive the equilibrium equations without using Newton's law, which is summation of forces equals ma, which I covered in one of the earlier lectures. So the energy approach is a very powerful approach to derive structural theories. It can also be used to derive heat transfer theories. So why we don't go ahead and now start deriving what is going on here moving forward. So you can see here that can apply Cauchy's relationship here. I'm going to just combine these two integrals, but I want you to realize I can apply Cauchy's relationship here to relate the tractions to a cube inside the body, because that's where failure could occur. So I want to draw a free diagram there to proceed forward. So that's sigma ij, and then I have del ui or nj del ui, and here as well. I'm going to combine these integrals because I can. You can combine two integrals, and we know this one is 0, but it doesn't matter. I can still combine them. Okay, so we've done that. And now I'm going to apply Gauss theorem, which I've done several times by integrating by parts over and over and over. And what Gauss theorem is doing is taking a surface integral and converting that into volume integral. Very powerful idea. And in reverse, you're basically integrating by parts. That's all you're doing there. You're integrating by parts. So then I have this is equal to V. And then I'm going to combine this integral with that integral. And I'm going to have BI minus rho UI double dot. And then this one right here becomes a volume integral. And that volume integral is plus sigma ij del UI. And this comma j here becomes a comma j here. Okay. And then this is the volume. I want you to notice here how, and yeah, so we got in this far. So now I have to transfer this comma j over to this here. So I get integral v bi minus rho ui double dot plus sigma ij comma j. And then I have del ui, and the del ui factors out. So I have a significant mistake here that needs to be taken care of. So let's look at that mistake carefully. So this del ui was missing altogether everywhere. So I had to really bring that over here, and I had forgotten it. So I apologize for that. The mistake I made is actually even greater than I thought. So you can see here that, let me erase this. Each of these should have a del ui. So I apologize. Let's do it step by step. So this should have a del ui minus rho ui double dot del ui. And then this term right here becomes plus sigma j del ui. I had to remember I had that del ui already. So comma j here, and then close the dv there. And so now I'll continue. So I converted that surface integral into this volume integral using Gauss theorem. So I'll now transfer this comma j over to each of these using the product rule. So I have bi minus, and I will write the del ui again. So everything step by step. Minus rho ui double dot del ui, and I'll continue, plus sigma j, comma j, del ui, plus sigma j, del ui, comma j, notice that, dv. And so I can factor out del ui here, and I'll do that in the next page. So I have the external virtual work done is equal to the integral, and I'll factor del ui wherever I can, and you can see that I get bi minus rho ui double dot plus sigma j comma j, and then I have this interesting mysterious term that we've seen before, which is sigma j del ui comma j dv, and I already showed you in a previous lecture that this can be decomposed into sigma j, and that's on the deformed configuration. So this works for finite deformation theory. It just says on the deformed configuration. And so the strange for this is going to become 1/2 del ui comma j plus del j comma I plus 1/2 del ui comma j minus del u j comma I. And you can see you'll get the same answer we got before. Well, guess what? this right here is a rotation tensor. So that's del omega j, and this is del epsilon ij, infinitesimal strains on the deformed body. Very powerful idea, because I want you to also notice that this right here then is sigma ij del epsilon ij, okay, plus sigma ij del omega ij. But this is zero because we demonstrated that a symmetric tensor multiplied by a skew symmetric tensor gives you zero. And so the external virtual work done then can be represented. I'll continue now, I'll show you. But isn't this the equilibrium equations? They came out naturally here. You can see them. I didn't do any tricks. I didn't do any magic tricks. These are the equilibrium equations of elasticity. But I know that that's equal to zero, so I'll set it equal to zero for now, because I know it's zero. And what I've demonstrated is that the external virtual work, including the inertial effects, can be represented as the integral over the volume bi del ui dv, okay? And then I have the virtual work done due to the traction forces, Ti, okay? And then we've demonstrated, and I'll even include the inertial forces, which is okay to do. I'll do that here. That's okay to do that. And I've demonstrated that this is actually equal to the internal virtual work done. And the internal virtual work done is the stresses moving through infinitesimal strains. Very powerful idea. We've demonstrated that internal virtual work equals the external virtual work. In other words, we demonstrated that when I apply tractions, body forces, inertial forces, and when they move through virtual deflections, virtual displacements, that external virtual work is equal to the internal virtual work, which is the stress moving through the infinitesimal virtual strains. That's a very powerful idea, because that demonstrates, actually, you can use this to demonstrate different structural theories, and I'll show that in a minute. So the thermal virtual displacements, or the principal virtual work, also called PVW. What this theory says is the following way. It says, and I'll write exactly how it was demonstrated um, originally. It says the static field in a deformable body is statically admissible if and only if the total external virtual work is equal to the total internal virtual work for every kinematically admissible field. In other words, I'll just simplify this for you very simply. The principal virtual work states that for every static field, in other words, for every structural body that has deformed, due to laws applied, due to body forces, traction forces, inertial forces, that body is in static equilibrium. And that only happens if the external virtual work equals to the internal virtual work. Very powerful idea, because I will show you in a second that this actually implies that the body is in equilibrium, and it's going to give you the same answers we got before in a lot more complicated manner. And I'll show you that in a second, because this is a and I'm going to show you, in fact, that we have not used Newton's law to derive these equations, yet we get the equations from Newton's law. So why we don't now derive starting? So now this is a principle. From now on, you have to use this principle. And that's where calculus variations comes into play. I want to show you how to move forward in the future when you use the principle of virtual work. The principle of virtual work, you're always going to start with any structural theory, and I'll repeat it once again. The step number one is to invoke the principle of virtual work. Invoke, and I'm going to cover 3D theory now. This is the most general theory that you can ever have. And this 3D theory is true for finite deformation, and we can demonstrate again that this could work on the undeformed configuration using the second polar Kirchhoff stress, which is energetically conjugate to the virtual green Lagrange strain. But I'm not going to go there because it's not necessary. This also works, and that's okay. That's okay. Let's invoke the principle of virtual work. PVW. I'll be using PVW quite a bit, which is principle of virtual work. And let's start invoking it. Let's invoke it now. The principle of virtual work states that the external virtual work equals the internal virtual work. That's your first step. I'm going to derive the 3D theory right now, remember. That's what I'm doing in this step. The principle of virtual work states that the external virtual work equals the internal virtual work. And we're going to apply this theory over and over and over to various theories, structural theories. You can also apply something very similarly analogous to heat transfer and moisture diffusion problems and chemical problems, chemistry problems. So there's this is parallel to other theories that you can develop in other disciplines. But we're going to stick in structural theories for now, since it is, you can physically understand what's going on. So we invoke the principle of virtual work. The external virtual work equals the internal virtual work. And so I'll invoke it. Every time that you do this, you will have to write all the terms. And all the terms look like this. Ti, n, del ui, ds, plus the body forces, del ui. Again, you don't have to memorize any of this, because you should know that tractions moving through the deflections, virtual displacements, gives you a virtual work quantity. And that's external forces, obviously, because we are looking at external forces acting on this body, Bi, and then tractions applied here, for example, Ti. So very clearly that is going on. And I also could have accelerations as well, as I said before, and that's acting on the body as well. Minus volume rho ui double dot del ui d volume. And we already demonstrated this principle of virtual work clearly states that this is equal to the internal virtual work, which is the integral over the volume of the Cauchy stress tensor sigma ij, which acts on the deformed body, times the virtual strain, infinitesimal strain, on the deformed body. And again, this works for finite deformation. And we demonstrated already. So after you get to this step, what you want to do is substitute what epsilon ij is. That's your next step. Step number 2, calculate strains for that theory. Calculate strain for that theory. Well, for the 3D theory, we know that epsilon ij is equal to 1/2 ui comma j plus uj comma I. We know that. And it should be very apparent to you based on all the work we've done on this. We've shown this over and over and over. And you can continue on with this, and I apologize. So then I've also demonstrated, and you know, we can continue on. So this is the integral. What I'll do is apply here on the left side. I apologize for that. I'm just writing all the quantities to the left hand side. And I have minus the integral over the volume sigma ij, and then 1/2. I apologize for that. There was a little noise out here. I think it was a squirrel. I apologize for that. I'll continue. So 1/2 del ui comma j plus 1/2 u del u. Sorry about that again. dv. So that's what I get. And I want you to notice that since the stress tensor is symmetric, and this del uij and I and j are summation indices, since the stress tensor is symmetric, it doesn't really matter. When you bring everything together, this becomes integral over the volume sigma ij del ui comma j. Because I and j are summation indices. And the other way, if you're not convinced, you can expand this expression, putting summation in front, just expand it out. You're going to have 9 terms when you do it. And you're going to see that everything that has ui comma j and uj comma I, that those terms with sigma j will collapse and it will give you twice, so the 1/2 will disappear. I invite you to demonstrate this and send me an email showing me that you got it done. And you may have a nice surprise if you get it done. This is equal to 0 when I move this to the left-hand side. And step number 3 then, notice that everything has del ui except this one. So step number 3 is to integrate by parts to remove any derivatives on ui. So yes, let's do that. So that's the integral or the volume tin del ui ds. And let's say that these tractions are acting, and here I had them acting on the partial v1. So let's just make them acting on partial v1, if that's okay with you. That way it's clear that those tractions are only acting there, plus the integral v bi del ui. And I'm going to combine these two terms if that's okay, because I can. There's nothing going on there. Minus rho ui double dot del ui dv. And now I'm going to integrate this by parts. And you learn how to integrate parts because we've done it over and over and over. And I think I'll just do it here so you can see it one more time. So sigma j del ui comma j. Remove the j, put it on the other side. And then draw a plus sign and a minus sign. And remember that because a volume integral, when you integrate parts, you get a surface. So you must have an nj here that corresponds to that. And so then the cross term becomes a surface integral, while the term here at the bottom becomes a volume integral. So let's start with the volume integral. And remember, I had a minus here. So that minus times this minus here gives you plus. So that's plus the integral over the volume sigma ij, comma j, del ui dv. And then I have the traction terms. This cross term here is the surface integral. So I have minus now, look at this very carefully, minus of over the whole surface. But I'm going to divide into two surfaces, if that's okay with you. It's just easier to visualize what's going on. Sigma j and j del ui dv. And you're going to freak out. I think you're going to freak out when you see what's going to happen, because I will have derived and over the surface 2 sigma ij nj del ui dv equal to 0. And let me move all this to the top so it's not congested at the bottom so you can see it better later. So I'm going to integrate parts here in this box, sigma j del ui comma j, and then I have sigma j comma j del ui plus minus, and that's nj, and that's what I did. And sorry for that, it got cramped, but this is very, very powerful. Let's look at this. Everything has dv can be combined. So let's combine this and this. So that's the only ones that are dv. This is a surface integral, so that's a mistake, ds. I apologize. This term can combine with this term. And so let's go to the next page, in a blank page, and show you how everything combines. So I have the integral over the volume, bi minus rho ui double dot plus sigma ij comma j I apologize for that, dv. So I combine all the terms together, and remember these del ui dv. And now I have the surface integrals that combine. So I have plus the integral over the part of the surface of the volume, which is tin. And notice how this term right here combines with the term here. So that's sigma ij minus sigma ij nj del ui ds. And then I also have then this term right here that's left out, minus, and so then I have this term here at the end, which is minus partial v2, and then I have sigma. So what do I have? I have sigma ij nj del ui ds equals 0. Now, very powerful idea. Very powerful idea, because now I can apply the calculus variations. So now I have 1, 2, 3. 1, invoke the principle of virtual work. This is always true for structural body. Step number 2, calculate the strains for that particular theory. 3D, this is the most general strain that you can have. Then substitute it in, integrate it by parts to remove any derivatives on the displacements. And once you get there, this is what we got. We integrate our parts and we combine all the terms together. This is very powerful because now I can invoke the fundamental lemma of calculus of variations, which tells you that for any arbitrary del ui was in the integrand must be equal to 0. Well, this is a volume integral. So therefore, bi minus rho, and I'll just write it out as you've seen it before. This in V, in the volume V. So there's a volume V. This equation is true for every point in the volume. That's what that's saying. And then I look at the second integral. That's a surface integral. These are the boundary terms. These are the boundary terms, right? These are the boundary terms. And the boundary terms tells us on the surface, it tells us that on just V1, just on this one here, where I had tractions applied, and these are the surface here, this is specified, the deflections, so that's del partial V2, and the rest of the surface from here to there and from here to here, I'm calling del V1, and that's where tractions are applied. Look at this powerful thing here. We get a TIN equals sigma ij and j. And then on surface V2, I get, now on surface V2, you tell me, in that surface, the deflections are specified. Isn't del ui 0 at that location? Because I've specified it. I know what it is, so therefore I cannot vary it. So therefore del ui is 0, so therefore ui has been specified. And I will never want to see anybody write del ui equals 0 here because that's incorrect. What I want to see is you writing ui equals ui bar. That's what I want you to see you do. And so what is so powerful about this? Let's think about it for a second. I started the principle of virtual work, number one, step number one. And I ended up with the equilibrium equations of elasticity. I ended up with equilibrium equations of elasticity, which I had first derived using Newton's law, the integral form of Newton's law. In physics, they taught you F equals ma. In my class, I taught you a more general standpoint, which is using the integral form of Newton's law for a deformable body, and we arrived to this equation. But now I arrive to this equation in a different way. I arrived to this equation using the principle of virtual work. Secondly, if you recall, I derived Cauchy's stress relationship. I derived Cauchy's stress relationship using the tetrahedral element. And when I did that, it looked quite complicated. It took me a while to get there. Guess what? I got it naturally. I didn't have to even try hard. I just got it here. I got Cauchy's relationship here without even trying by using just Gauss Theorem, which is just a mathematical way of integrating by parts. Secondly, I automatically got the deflections, the displacements for this system. So in other words, for 3D theory, I just derived for you the most complicated theory, which is 3D theory. That's the most general theory. And I found the equilibrium equations of elasticity. And I found the deflections. And I found Cauchy's relationship. I want you to meditate on this a little bit because I want you to really understand the miracle of what we have done. It is a true miracle because we've derived what we found through Newton's law, but now we derive it using the principle of virtual work. And I plan to use these calculus variations techniques to derive new structural theories or structural theories that have been documented, but I'm going to walk you through several theories. And these approaches are used quite significantly in the derivation of structural theories. And so that's why it's so important for you to understand these basic 4 steps. With that said, I want you to really write all this stuff down and fully understand it. Have a good day.